Imagine looking up at the night sky, vast and endless, dotted with shimmering stars, each one part of something far grander than what meets the eye. But what if I told you some of the most fascinating secrets of the cosmos aren't hiding in those bright, sprawling galaxies we often picture? Instead, they're tucked away in the smallest, most unassuming corners of the universe, dwarf galaxies. These tiny cosmic neighborhoods, often overshadowed by their larger cousins, hold mysteries so strange, so utterly baffling, that they've left astronomers scratching their heads for decades. And today, we're about to uncover 25 of their most mind-bending secrets, discoveries that defy logic, challenge our understanding of space, and might even rewrite the rules of the cosmos as we know them. Dwarf galaxies are the universe's underdogs, small, faint, and often overlooked, yet packed with more intrigue than a sci-fi thriller. Unlike the majestic spirals or glowing ellipticals we see in textbooks, these galaxies are modest in size, sometimes containing just a few billion stars compared to the hundreds of billions in giants like our Milky Way. But don't let their size fool you. What they lack in grandeur, they make up for in sheer weirdness. Some are nearly invisible, cloaked in dark matter. Others seem to break the laws of physics, moving in ways that shouldn't be possible. And then there are those that appear to be missing something crucial, like the galaxies that somehow exist without dark matter altogether, throwing decades of astronomical theory into chaos. So why should we care about these cosmic oddballs? Because they're more than just celestial curiosities, they're time capsules, holding clues to the universe's earliest days. They're laboratories testing our wildest ideas about gravity, dark matter, and even the birth of stars. And most thrilling of all, they're proof that the universe still has secrets left to spill. Over the next few minutes, we'll journey through the strangest, most head-scratching discoveries about dwarf galaxies, from ghostly structures that shouldn't exist to bizarre behaviors that science still can't fully explain. By the end, you'll see the night sky in a whole new light, and trust me, you'll never look at these tiny galaxies the same way again. So buckle up, the cosmos is about to get a whole lot weirder. Picture a galaxy so faint, so wispy, that it barely registers against the black canvas of space. A cosmic ghost made of stars scattered so thinly, you could fly through it for light years without spotting a single one. These are ultra-diffuse galaxies, and they're among the most puzzling discoveries in modern astronomy. First stumbled upon in the 1980s, these galaxies weren't taken seriously at first. Many astronomers dismissed them as glitches or artifacts in their observations. But as telescopes grew more powerful, the truth became undeniable. These faint, sprawling structures were real, and they shattered every expectation of what a galaxy should look like. Unlike the dense, glittering hubs of stars we're used to, ultra-diffuse galaxies are almost transparent, with stars spread so far apart that some are even less dense than the space between galaxies. Take Dragonfly 44, one of the most famous examples. It's as wide as the Milky Way but contains just 1% of its stars. That's like stretching a single handful of sand across an entire beach. Even stranger, many of these ghostly galaxies are found lurking in galaxy clusters, chaotic environments where gravity should have torn them apart long ago. Yet there they are, defying destruction like cosmic phantoms. The real shock came when scientists tried to explain how these galaxies exist at all. Traditional models suggest galaxies form from collapsing gas clouds, with gravity pulling stars tightly together. But ultra-diffuse galaxies seem to ignore those rules. Their stars are too few, too spread out, and yet they hold together somehow. Some theories point to dark matter acting as an invisible scaffold, giving these galaxies just enough structure to survive. Others propose they're failed galaxies, ones that started forming stars but ran out of gas literally. But the most mind-bending idea, that they're the ancient remnants of violent cosmic collisions, galactic debris stretched thin over eons. What makes these faint giants so important isn't just their strangeness, it's the questions they force us to ask. If our theories can't fully explain ultra-diffuse galaxies, what else might we be missing? Are there even fainter, weirder galaxies hiding in plain sight, waiting to upend our understanding of the universe? Every time we think we've got space figured out, discoveries like these whisper, "Think again." Now let's shift our gaze to one of the most baffling revelations about dwarf galaxies, the fact that some of them are almost entirely made of something we can't even see. Dark matter, that mysterious substance that outweighs visible matter in the universe 5-1, doesn't just linger in the background of these tiny galaxies, it completely dominates them. Take Segue 1, a dwarf galaxy orbiting the Milky Way. At first glance, it appears as nothing more than a faint smudge of stars, barely noticeable against the cosmic backdrop. But when astronomers measured its mass, the numbers didn't add up. The gravitational pull suggested something far heavier than the handful of visible stars could explain. In fact, calculations revealed that dark matter makes up a staggering 99% of Segue 1's total mass. That means the stars we see are just the tiniest sprinkles on an invisible cosmic iceberg. How do scientists even measure something they can't see? It all comes down to gravity's fingerprints. By tracking the movements of stars within these galaxies, researchers can calculate how much mass must be present to keep them from flying apart. In normal galaxies, stars and gas account for most of that pull. But in dark matter-dominated dwarfs, the stars move at speeds that would be impossible unless an enormous, unseen force were holding them together. The discrepancy is so extreme that in some cases, for every one sun's worth of visible matter, there are thousands of suns worth of dark matter lurking in the shadows. This discovery turned our understanding of galaxy formation upside down. Dark matter was always thought to be the scaffolding that galaxies grew around, but these dwarfs suggest it can also call the shots, dictating how galaxies behave even when almost no regular matter is present. And that raises a spine-tingling question. Could there be galaxies out there made entirely of dark matter with no stars at all? Some researchers think so, pointing to bizarre gravitational anomalies where nothing visible exists to cause them. The implications stretch far beyond these small cosmic curiosities. If dark matter can form structures without stars, it challenges our models of how the universe evolved after the Big Bang. It also forces us to reconsider what a galaxy even is. Does it need stars, or is gravity alone enough? Every time we peer into these faint, enigmatic dwarfs, we're not just studying tiny galaxies, we're decoding the hidden architecture of the cosmos itself. But here's where things get really strange. Our universe might be missing something, or rather, it's missing a lot of somethings. According to our best theories, giant galaxies like the Milky Way should be surrounded by swarms of dwarf galaxies, thousands of them, orbiting like cosmic fireflies. But when astronomers actually went looking, they barely found a few dozen. This glaring mismatch between prediction and reality has a name: the missing satellite problem, and it's one of the most persistent headaches in modern astrophysics. The roots of this mystery go back to the very foundation of our understanding of the cosmos. Simulations based on the leading model of the universe, dark matter, and all show that when massive galaxies form, they should pull in countless smaller dwarf galaxies along the way, like a king surrounded by an entire court of tiny attendants. Yet when we peer at our own Milky Way or our neighbor Andromeda, the numbers just don't add up. The discrepancy isn't slight either. We're talking hundreds, maybe even thousands of dwarfs that should be there but aren't. So where did they all go? One possibility is that we're simply not seeing them. Some of these missing dwarfs could be so faint, so utterly drenched in darkness that our telescopes just can't pick them up yet. There's precedent for this. Remember those ultra-diffuse galaxies we talked about earlier? If even a fraction of the missing satellites are that ghostly, it would explain why they've been so elusive. Another theory suggests they never formed in the first place. Maybe the extreme gravity of the larger galaxy shredded them before they could fully develop, leaving behind only scattered stars as cosmic breadcrumbs. But the most tantalizing idea, and the one that keeps scientists up at night, is that our understanding of dark matter itself might be flawed. What if dark matter behaves differently on small scales than we've assumed? Some researchers are exploring tweaks to the standard model, proposing that dark matter might be warmer or even interact with itself in ways we don't yet grasp. Others wonder if we're seeing the fingerprints of an entirely new physics, something lurking beyond our current theories. Here's what makes this debate so thrilling. It's not just about counting missing galaxies. The missing satellite problem is a direct challenge to the very framework we use to explain the universe's structure. Every time we find or fail to find one of these dwarfs, we're not just solving a puzzle, we're stress testing the foundations of cosmology itself. And that's the beauty of science sometimes. The absence of something can be just as revealing as its presence. If there's one thing dwarf galaxies refuse to do, it's follow the rules, especially when it comes to making stars. While grand spirals like our Milky Way churn out new stars at a steady, predictable pace, dwarf galaxies are the cosmic rebels, flipping between explosive bursts of creation and eerie billion-year slumbers. Take the small Magellanic Cloud, one of our closest galactic neighbors. In most galaxies, star formation is a gradual process, like a slow-burning campfire. But this dwarf galaxy operates more like a firework, suddenly lighting up with frantic starbirth, then fading back into near-total silence. Astronomers have spotted clusters of young, massive stars here that formed in a single, violent burst, as if the galaxy decided to cram millions of years of activity into a cosmic blink. What causes these wild swings? The answer lies in the delicate dance between gas, gravity, and chaos. Unlike larger galaxies, dwarfs lack the sheer mass to hold onto their gas tightly. A passing interaction with another galaxy, or even a ripple from a nearby supernova, can send shockwaves through their sparse reservoirs of star-forming material. Suddenly, pockets of gas collapse all at once, igniting a frenzy of new stars. But there's a catch: these bursts are self-destructive. The very stars they create unleash powerful winds and radiation, blowing the remaining gas away like cosmic confetti. With their fuel supply scattered, the galaxy has no choice but to shut down production, sometimes for billions of years, until enough gas drifts back to start the cycle again. The quirks don't stop there. Some dwarf galaxies, like Leo T, exist in a bizarre twilight state, barely forming stars at all, yet not quite dead. They cling to tiny amounts of gas, just enough to produce the occasional star every few 100 million years, like a flickering candle in the dark. Others, like ultra-faint dwarfs, seem to have burned out entirely in the universe's youth, their star-forming engines shutting down so early that they're essentially frozen relics of the ancient cosmos. Why does this matter? Because these erratic bursts and pauses are more than just cosmic mood swings, they're time capsules. The long dormant periods mean some dwarfs preserve chemical fingerprints of the early universe, untouched by later generations of stars. Their stop and start rhythms also challenge our models of how galaxies evolve. If star formation can turn on and off like a sputtering faucet, what does that say about the fate of larger galaxies? Could the Milky Way's steady production be the exception, not the rule? Perhaps most intriguingly, these patterns hint at a universal truth: size isn't everything. A galaxy doesn't need to be vast to be dramatic. In the grand tapestry of the cosmos, it's often the smallest players that hold the most surprising scripts. In the violent chaos of colliding galaxies, where stars are flung like sparks from a cosmic forge, something extraordinary can emerge from the wreckage: a tidal dwarf galaxy. Unlike traditional galaxies born from collapsing gas clouds, these celestial oddballs are stitched together from the shredded remains of larger galactic collisions, pulling themselves together from the debris like cosmic phoenixes rising from the ashes. Picture the antennae galaxies, two spirals locked in a gravitational dance so fierce that their mutual pull rips out vast streams of gas and stars. Amid that chaos, clumps of material begin to coalesce, not under the grip of dark matter, but purely through the gravity of the visible matter they contain. The result, a newborn galaxy with a family tree unlike any other. What makes tidal dwarfs so baffling is that they defy the usual cosmic hierarchy. Most galaxies, big or small, owe their structure to dark matter. It's the invisible glue that holds them together. But tidal dwarfs are different. They form from the leftovers of collisions, meaning they're made almost entirely of regular matter. Stars, gas, and dust, with little to no dark matter in the mix. This turns our understanding of galaxy formation on its head. Take NGC 769-3, a tidal dwarf in the famous Stephan's Quintet. Observations show it moves too slowly for a typical dark matter-rich galaxy, yet it holds itself together perfectly fine. How? Because it's bound by the gravity of the stuff. We can actually see a rarity in a universe dominated by the invisible. Then there's the identity crisis they create. Galaxies are usually classified by their shape: spirals, ellipticals, irregulars, but tidal dwarfs blur those lines. Some look like messy splotches of stars, while others develop faint spiral arms or even disks, mimicking their larger cousins. Take the Magellanic Bridge, a ribbon of gas connecting the large and small Magellanic Clouds. Nestled within it are tiny stellar clumps, tidal dwarfs in the making, each one a cosmic patchwork quilt of recycled material. Are they true galaxies or just temporary features? The debate rages on because, unlike traditional dwarfs, these objects might not survive for billions of years. Some could disperse back into the void, while others might merge into something new. The real kicker: tidal dwarfs aren't just curiosities, they're time machines. The gas they're made from is often pristine, untouched by the pollution of generations of stars. That means they offer a snapshot of the raw materials that built the universe. And because they form so violently, they're stellar nurseries on overdrive, birthing stars at rates that put most galaxies to shame. The implications are staggering. If tidal dwarfs can form and thrive without dark matter, could there be other galaxies out there playing by different rules? And if so, what does that say about the countless normal galaxies we thought we understood? Every collision we witness isn't just destruction, it's creation in disguise. And in the tangled debris of these cosmic crashes, tidal dwarfs whisper a humbling truth. The universe is far more inventive than we ever imagined. Out in the cosmic void, far from the bustling crowds of galaxy clusters, drift the loners of the universe, isolated dwarf galaxies. These solitary wanderers shouldn't exist, at least not according to our traditional models of how galaxies form. Imagine a tiny village thriving in the middle of an endless desert, with no roads, no rivers, no connections to the outside world. That's the enigma of these isolated dwarfs. While most dwarf galaxies orbit larger hosts like the Milky Way, clinging to them like moons to a planet, these renegades float completely alone in the vast darkness, some separated from their nearest neighbors by millions of light years. And their very existence is forcing astronomers to rewrite the rules of cosmic evolution. Take K248-1, a dwarf galaxy drifting in the emptiness between the local group and the next cluster of galaxies. It's not just far from other galaxies, it's staggeringly, almost unnervingly alone. According to conventional theory, galaxies like this should be cosmic stillbirths. The dominant idea suggests that dwarf galaxies form in the gravitational shadows of larger ones, where dense pockets of dark matter create nurseries for stars. Without a massive galaxy nearby to provide that initial scaffolding, there simply shouldn't be enough raw material for a dwarf to coalesce. Yet there they are, these defiant little islands of light glowing in the wilderness. So how did they get there? One possibility is that they're refugees, violently ejected from galactic clusters long ago. Simulations show that during colossal collisions between galaxies, the gravitational chaos can fling smaller dwarfs clear out of their orbits, sending them hurtling into the void like cosmic slingshots. Another, even wilder idea is that these isolated dwarfs formed in place from gas clouds so dense they managed to collapse without the usual dark matter boost. That would mean the universe has more than one recipe for galaxy formation, a revolutionary notion that could upend decades of astrophysics. The real surprise came when astronomers studied the chemistry of these loners. Many are brimming with heavy elements, the kind typically forged in the hearts of massive stars and scattered by supernova. But in isolated dwarfs, there's no nearby galaxy to explain where those elements came from. That suggests these tiny galaxies once hosted their own violent bursts of star formation, all on their own. Some even show signs of recent activity, as if they're still stubbornly churning out new stars against all odds. What makes these findings so thrilling isn't just the mystery, it's the implications. If dwarf galaxies can form and survive in complete isolation, it means our universe is far more inventive than we thought. Maybe dark matter isn't the only scaffold for galaxy birth. Maybe the void isn't as empty as it seems. Every time we spot another of these cosmic hermits, it's a reminder the universe doesn't play by our rules. It writes its own. If you think dwarf galaxies are just smaller versions of the Milky Way, think again. Some of them have chemistry so bizarre, it's like finding a cave painting in a modern art museum. Take a deep breath, because we're diving into one of the most startling revelations about these cosmic oddballs, their utterly alien chemical makeup. While most galaxies are peppered with heavy elements like carbon, oxygen, and iron, the cosmic metals forged in stellar furnaces, certain dwarf galaxies are almost eerily pristine, as if they've been frozen in time since the universe's earliest days. The most extreme examples, like the dwarf galaxy Segway 1, contain as little as 1,000th the metal content of our Sun. That's not just different, it's a window into a universe before metals even existed. How does a galaxy end up so chemically primitive? The answer lies in their stunted star-forming history. Heavy elements are created inside stars and scattered across space when those stars explode. But some ultra-faint dwarfs barely had any stars to begin with, and those that did formed in a single, fleeting burst before the galaxy shut down entirely. Without subsequent generations of stars to enrich their gas with metals, these galaxies became cosmic time capsules, preserving conditions nearly identical to the universe's infancy. Imagine stumbling upon a village untouched by modernity, where every tool and artifact hails from the Stone Age. That's what observing these metal-poor dwarfs is like for astronomers. But the anomalies don't stop there. Some dwarfs, like the Small Magellanic Cloud, are bizarrely uneven in their metal distribution, patches of near-primordial gas sitting alongside regions that are oddly enriched. This patchwork suggests chaos in their past, mergers, collisions, or bursts of star formation that never quite spread evenly. Even stranger are the rare dwarfs like Izwiki 18, which, despite their advanced age, have metal levels so low they resemble galaxies from the universe's first billion years. It's as if these galaxies hit the cosmic pause button, skipping eons of chemical evolution entirely. What makes these chemical ghosts so valuable isn't just their strangeness, it's the clues they offer about the universe's raw ingredients. By studying their composition, we're essentially tasting the cosmic soup from which all galaxies formed. Their scarcity of metals hints at how inefficient early star formation must have been, with only a handful of stars lighting up the darkness. Some even contain elements in ratios that defy our models of supernova explosions, suggesting the first stars died in ways we've never witnessed. Perhaps most tantalizing is what these dwarfs imply about the hunt for the universe's very first stars. These hypothetical population 3 stars, massive pure hydrogen giants that have never been observed, might have left their fingerprints in the metal-poor dwarf's gas. If we can decode those faint chemical signatures, it would be like uncovering fossils of the cosmos's first light. Every atom in these galaxies is a silent witness to the universe's most violent and creative moments, and they're whispering secrets we're only beginning to hear. In the cosmic menagerie of dwarf galaxies, few creatures are as enigmatic as the ultra-compact dwarfs, tiny, blazing knots of stars so dense they defy classification. Picture a globular cluster, those ancient spherical swarms of stars orbiting galaxies like bees around a hive. Now imagine one that's somehow packed with 10 times the stars, blazing with the brightness of a miniature galaxy, yet crammed into a space barely larger than a typical cluster. That's the paradox of ultra-compact dwarfs, too massive to be mere clusters, yet too small to fit the traditional galaxy mold. Discovered accidentally in the late 1990s while astronomers were surveying the Fornax galaxy cluster, these objects were initially dismissed as glitches or foreground stars. But as observations sharpened, the truth became undeniable. They were something entirely new, and they've been rewriting cosmic rulebooks ever since. Take M60 Satellite 1, one of the most studied ultra-compact dwarfs. It's only about 120 light-years across, a speck compared to the Milky Way's vast 100,000 light-year span, yet it contains over 10 million stars, shining with the collective light of 20,000 suns. That density is staggering. If you stood on a planet in its core, the night sky wouldn't just be dotted with stars. It would blaze with a continuous carpet of light, like standing inside a cosmic jewel box. But here's where it gets weird. Despite their star-packed cores, many ultra-compact dwarfs are surrounded by mysterious halos of dark matter, a feature unheard of in ordinary star clusters. This eerie gravitational shadow suggests they might be the stripped-down remnants of once larger galaxies, their outer layers torn away by violent encounters, leaving only their dense hearts behind. The puzzle deepens when you examine their origins. Some ultra-compact dwarfs, like Omega Centauri, long thought to be a mere cluster, show chemical variations among their stars, hinting at multiple generations of star formation. That's a galactic trait, not a cluster one. Others, like Vuct-3 in the Virgo cluster, move with the serene confidence of objects far heavier than their visible stars suggest, again pointing to unseen dark matter anchoring them. Then there's the bizarre case of M85 Cluster 1, which orbits a galaxy in the Virgo cluster. It's not just dense, it's racing through space with enough speed that, by all rights, it should have escaped its host galaxy's grip long ago. Yet there it remains, as if held by invisible hands. What makes these cosmic conundrums so thrilling isn't just their defiance of categories, it's the questions they force us to ask about the very nature of galaxies. Are ultra-compact dwarfs the stripped cores of cannibalized dwarfs, as some theories suggest? Or could they be primordial building blocks of the universe, surviving relics from an era when mini-galaxies collided and merged to form the giants we see today? Even their lifespan is a mystery. In the crowded environments of galaxy clusters where gravitational tugs are constant, many ultra-compact dwarfs might eventually be ripped apart, their stars scattering like grains of sand in the cosmic tide. Others could endure for billions of years, silent witnesses to the universe's unending dance. Every time we study these dense stellar enigmas, we're reminded that the universe resists neat labels. In the twilight zone between star clusters and galaxies, ultra-compact dwarfs challenge us to rethink what it means to be a galaxy at all, and in doing so, they reveal just how much we still have to learn about the cosmos's smallest yet most defiant inhabitants. The universe isn't just expanding, it's also a battlefield where galaxies wage silent wars of cosmic consumption. And in these clashes, dwarf galaxies often pay the ultimate price, being torn apart piece by piece by their ravenous larger neighbors. This brutal process, known as galactic cannibalism, isn't some distant theoretical idea, it's happening right now in our own cosmic backyard. Look at the Sagittarius dwarf spheroidal, a tiny galaxy locked in a death spiral around the Milky Way. Over billions of years, our galaxy's gravity has stretched it into a shimmering ribbon of stars, a ghostly tidal stream wrapping around the Milky Way like celestial tinsel. What was once a cohesive galaxy is now little more than stellar debris, its stars scattered across the heavens, a cosmic meal in progress. But how does this dismantling happen? Imagine a snowball passing too close to a blowtorch. The outer layers melt first, streaming away in delicate tendrils. That's precisely what occurs when a dwarf galaxy ventures too close to a giant. The larger galaxy's gravity creates tidal forces, unstoppable pulls that stretch the dwarf stars and gas into long, glowing arcs. Some of this material gets flung into deep space, while the rest is siphoned into the larger galaxy's embrace. The result, stellar theft on an unimaginable scale. The Milky Way, for instance, has likely absorbed dozens of dwarfs this way, their stars now indistinguishable from our galaxy's native population. The evidence isn't just theoretical, it's written across the sky. In the Andromeda galaxy's outskirts, astronomers have spotted vast, looping structures called tidal streams, the shredded remains of dwarfs caught in its gravitational web. One of the most dramatic examples is the giant stellar stream, a river of stars spanning nearly 200,000 light-years, the skeletal remains of a galaxy devoured long ago. Even more haunting are the so-called ghost galaxies, like Triangulum 2, which show signs of being actively ripped apart, their stars bleeding into the void like cosmic ink in water. What makes this process so fascinating isn't just the destruction, it's the unintended creativity. As dwarfs are dismantled, their stolen stars don't just vanish. They form intricate structures within their captors, stellar halos, warped disks, even new star clusters. Some researchers believe the Milky Way's enigmatic Gaia sausage, a vast collection of stars orbiting in chaotic paths, might be the mangled core of a dwarf galaxy swallowed nearly 10 billion years ago. These stellar fossils tell a violent history, one where growth comes from collision and rebirth emerges from destruction. But here's the twist, not all dwarfs go quietly. Some, like the Large Magellanic Cloud, are massive enough to fight back, distorting their captor's shape in return. Others, like the ultra-faint dwarfs, are so diffuse that they dissolve almost without a trace, leaving behind only the faintest trails. And then there are the dwarfs that cheat death entirely, those flung into wide orbits, destined to circle their predators for eternity, just out of reach. This relentless cycle of consumption raises profound questions. Are all galaxies built this way, stitched together from the corpses of their smaller kin? If so, the Milky Way isn't just a galaxy, it's a graveyard, a cosmic quilt woven from stolen stars. And perhaps most chillingly, one day, even our galaxy will face the same fate when it collides with Andromeda. The universe doesn't play favorites. In the end, size wins, and the dwarfs are always the first to go. If galaxies had a VIP section, supermassive black holes would be the bouncers, cosmic heavyweights lurking in the hearts of nearly every major galaxy, governing the chaos around them. But step into the realm of dwarf galaxies and something peculiar happens. These gravitational titans are nowhere to be found. Despite decades of searching, astronomers keep coming up empty-handed. The absence is so glaring it sparked a cosmic whodunit. Where are the dwarf galaxies' supermassive black holes, and why does their disappearance threaten to rewrite what we thought we knew about galaxy evolution? The mystery begins with scale. In giant galaxies like the Milky Way, supermassive black holes are practically a given. Our own Sagittarius, a star, tips the scales at 4 million times the Sun's mass. Logic would suggest that dwarf galaxies, the smaller siblings of these cosmic giants, should host scaled-down versions of these monsters. But when researchers scoured thousands of dwarfs for the telltale signs, swirling gas, frenzied stars, or the X-ray glow of devoured matter, they found almost nothing. Only a handful of dwarfs, like the Leo First galaxy, show even a hint of hosting a central black hole, and even those are far smaller than predicted. The rest are eerily quiet, as if someone forgot to invite the universe's most notorious gatecrashers to the party. So where did they go? One theory suggests these black holes never formed in the first place. Unlike their massive cousins, which likely grew from seeds in the early universe, dwarf galaxies might have lacked the dense, gas-rich environments needed to nurture those seeds. Picture trying to grow a redwood in a desert without the right conditions. Even the mightiest beginnings will wither. Another possibility is far more violent mergers. When small galaxies collide, the gravitational chaos could eject their central black holes entirely, flinging them into intergalactic space like cosmic pinballs. Simulations show these rogue black holes drifting in the void, untethered to any galaxy, a haunting thought, considering there might be millions of them out there, invisible and alone. But the plot thickens when you consider the outliers, the rare dwarfs that do host black holes like Henni's 210, a tiny galaxy with a surprisingly active core. These exceptions hint that the rules might be more complex than we imagined. Perhaps black holes in dwarfs aren't missing, they're just sleeping, lying dormant without enough nearby matter to feast on. Or maybe they're hiding in plain sight, masquerading as ordinary stars until the right moment awakens them. The implications ripple far beyond these tiny galaxies. If supermassive black holes aren't an inevitable feature of galaxy formation, it challenges the very foundation of how we think cosmic structures evolve. Their absence also raises a tantalizing question. Could dwarf galaxies be the purest galaxies of all, untouched by the gravitational bullying of central black holes? Without these chaotic engines stirring their cores, dwarfs might preserve conditions closer to the universe's infancy, silent, serene, and free from the cosmic violence that shaped their larger cousins. Every time we peer into these unassuming galaxies, we're reminded the universe reserves its most profound lessons for the quietest corners, and in the case of the missing black holes, the silence speaks volumes. Now here's something that shouldn't happen, yet it does, over and over again, defying everything we thought we knew about how dwarf galaxies move. Picture a solar system where planets orbit the sun in a neat, flat plane like tracks on a vinyl record. That makes perfect sense. Gravity pulls everything into alignment over time. But galaxies, they should be different. Their satellites, smaller dwarf galaxies, ought to swarm around them in all directions like bees around a hive, pulled into chaotic orbits by the invisible hand of dark matter. Yet when astronomers looked closely at our Milky Way and its neighbors, they found something utterly perplexing. The dwarfs weren't scattered randomly, they were lined up, moving in a single, razor-thin plane around their host galaxy, as if strung on an invisible cosmic wire. This bizarre alignment, first noticed around the Milky Way in the 2000s, wasn't just a fluke. When researchers studied Andromeda, our closest galactic neighbor, they found the same thing, 11 of its dwarf satellites dancing in a synchronized disk, all orbiting in the same plane. The odds of this happening by chance, astronomers calculated it at less than 1 in 1,000. And it gets weirder, some of these dwarfs are even moving in harmony, like a school of fish gliding through space. Why does this shake the foundations of cosmology? Because dark matter simulations say it shouldn't be possible. According to our best models, dark matter halos, the invisible scaffolds that galaxies form within, should distribute dwarfs in a puffy, three-dimensional cloud, not a flat disk. It's like dropping marbles into a bowl of jelly. They shouldn't all settle neatly in a circle. Yet there they are, defying gravity's usual rules. So what's really going on? One radical theory suggests these aligned dwarfs might be cosmic newcomers, captured together from a passing filament of dark matter, a tendril of the cosmic web that snagged them like beads on a string. Others propose the dwarfs formed from gas ripped out of a larger galaxy during an ancient collision, leaving them orbiting in the same plane like scattered debris from a shattered window. But the most mind-bending idea, that dark matter itself might behave differently than we think. interacting in ways that create these ghostly alignments on scales we're only beginning to map. Every time we uncover another of these planar formations, it's a stark reminder. The universe doesn't just defy expectations, it rewrites them entirely. And in the silent, synchronized dance of dwarf galaxies, we might be glimpsing secrets of dark matter that no simulation could ever predict. Buried in the dim glow of dwarf galaxies are stellar relics so ancient they predate the Milky Way itself, living fossils from the universe's first chapter. While most galaxies recycle their stars over eons, these cosmic backwaters have preserved stellar populations nearly as old as time, offering us a direct glimpse into an era when the cosmos was raw, untamed, and utterly alien. Take the dwarf galaxy sculptor, a faint smudge orbiting the Milky Way. At first glance, it's unremarkable, a sparse collection of stars barely holding together. But peer closer, and you'll find stars with almost no heavy elements, a telltale sign they formed from primordial gas before supernova had seeded the universe with metals. These stars aren't just old, they're time machines, their chemical fingerprints unchanged for over 13 billion years. Why are these ancient stars concentrated in dwarfs? The answer lies in their stunted evolution. Unlike larger galaxies, which churn through generations of stars in a constant cycle of birth and death, many dwarfs experienced a single, explosive burst of star formation before settling into a near-permanent hibernation. Without subsequent generations to pollute their environment with heavy elements, they became cosmic museums, their earliest stars preserved in stellar amber. The ultra-faint dwarf Segway 1 takes this to the extreme. Its stars contain fewer metals than any known object in the universe, a mere whisper of the elements we take for granted on Earth. But the real treasure isn't just their age, it's what they reveal about the universe's first stellar generations. Astronomers suspect the earliest stars, called Population 3, were monstrous behemoths, hundreds of times the Sun's mass, burning hot and dying young in cataclysmic explosions. No Population 3 star has ever been observed directly, but their legacy lingers in the atmospheres of these ancient dwarf stars. By studying the faint traces of elements like carbon or iron in their light, researchers can reverse engineer the conditions of their birth. It's like finding ash in a prehistoric cave and deducing the shape of the fire that left it. The implications stretch far beyond stellar archaeology. These dwarfs challenge our timeline of cosmic dawn. Some, like Boots 1, host stars so pristine they must have formed shockingly early, perhaps within the universe's first few 100 million years. Others, like Tucana 2, stretch even further back, their stars hinting at a time when the first galaxies were little more than fragile knots of gas and dark matter. If confirmed, these findings could rewrite the story of how structure emerged from the primordial chaos. Yet the most haunting thought isn't about the past, it's about what still lies hidden. If dwarfs preserve stars this ancient, might some still shelter undiscovered relics, stars even closer to the universe's birth? Every time we train our telescopes on these faint galactic fossils, we're not just observing stars, we're decoding the very first pages of the cosmic story, written in light that's traveled nearly the entire lifespan of existence. Some dwarf galaxies don't just fade quietly into the cosmic night, they go out with a bang, unleashing winds so fierce they blast away their own future. These aren't gentle breezes, these are supersonic tempests, raging at thousands of kilometers per second, capable of sweeping an entire galaxy clean of the gas it needs to birth new stars. Picture a candle not just flickering out, but being snuffed by its own hurricane. That's the drama playing out in starbursting dwarfs like NGC 1569, where ferocious stellar explosions ignite winds powerful enough to reshape an entire galaxy's destiny. The chain reaction starts with star formation gone wild. Unlike the Milky Way's steady stellar production, some dwarfs experience brief, hyperactive bursts, creating massive stars dozens of times heavier than our Sun in a frenzy of cosmic construction. But these stars live fast and die violently, exploding as supernova within just a few million years. Each detonation sends shockwaves tearing through the surrounding gas, heating it to millions of degrees and propelling it outward in colossal waves. Multiply that by thousands of exploding stars, and suddenly you've got a galactic-scale wind, a firestorm of energy ejecting raw star-making material into the void. The numbers are staggering. In some dwarfs, these winds can expel 90% of a galaxy's gas reserves in under 100 million years, a blink in cosmic time. What's truly astonishing is how these self-destructive outbursts sculpt entire galaxies. Take IC-10, a small dwarf near the Milky Way. Observations reveal vast plumes of hydrogen gas streaming from its core, the smoking gun of a wind so powerful it's effectively sterilizing the galaxy. Without that gas, star formation grinds to a halt, leaving behind a dormant husk. But the violence isn't just destructive, it's creative. These winds enrich intergalactic space with heavy elements, seeding future generations of stars with the building blocks for planets and life. Some studies even suggest the Milky Way's outer halo might be sprinkled with metal-rich debris from long-vanished dwarfs that blew themselves apart, the real puzzle. Scale. Dwarf galaxies have such shallow gravitational wells that even a handful of supernova can launch gas clear into intergalactic space, something impossible in larger galaxies like Andromeda, where gravity's grip is too strong. That's why dwarfs like Markarian 71, despite their tiny size, can produce winds rivaling those of galaxies 100 times more massive. It's cosmic overkill. The smaller the galaxy, the more dramatic the fallout. Yet here's the twist: some dwarfs manage to recover. Deep radio observations reveal faint wisps of gas slowly falling back into galaxies like Didio 150, a sign that winds don't always mean total annihilation. Given enough time, billions of years, perhaps these galaxies might reignite their star-forming engines, which raises a tantalizing question. Could the Milky Way's own quiet dwarfs be the survivors of such violent pasts, their winds long stilled but their scars still hidden in the motions of ancient stars? The lesson written in these galactic gales is humbling. Even the smallest galaxies can wield forces mighty enough to alter their fate, and in doing so, they remind us that in the cosmos, size isn't everything. Sometimes the most powerful stories come in the tiniest packages. In the darkest corners of the cosmos, astronomers are chasing ghost galaxies that shouldn't exist, yet defy all logic by leaving their fingerprints across the universe. These aren't just faint dwarfs or dim clusters, they're something far stranger: dark galaxy candidates, cosmic mirages made almost entirely of dark matter, with barely a flicker of starlight to betray their presence. The first hints of these phantoms emerged in the early 2000s, when radio telescopes picked up vast clouds of hydrogen gas swirling with the motion of a galaxy. Yet when optical telescopes turned to look, there was almost nothing there. No stars, no glowing dust, just an eerie, invisible structure moving with the purposeful rhythm of a galaxy cloaked in shadow. Take Virgo Hydrogen 21, one of the most compelling dark galaxy candidates. This enigmatic object floating in the Virgo cluster contains enough hydrogen gas to birth billions of stars, yet somehow it's produced almost none. The gas spins in a perfect disk, just like a spiral galaxy's would, but apart from a handful of dim stars, the stage is empty. The only explanation, an immense halo of dark matter, silently orchestrating the motion from behind the curtain. Without it, the gas would have scattered into the void long ago. But here's the twist: despite decades of searching, we still can't prove these dark galaxies exist definitively. They're cosmic maybes hovering at the edge of detection. So how do you hunt something you can't see? Astronomers have turned to clever workarounds. Some study gravitational lensing, the way these invisible objects bend light from background galaxies, betraying their mass. Others scrutinize ripples in the cosmic web, where dark matter's gravitational waves might reveal hidden structures. but the most tantalizing clues come from rogue stars, lonely suns drifting in intergalactic space with no obvious home. These orphans might be the remnants of dark galaxies too faint to spot, their stars stripped away by tidal forces, leaving only whispers of their former selves. The implications are staggering. If confirmed, dark galaxies would force us to redefine what it means to be a galaxy at all. Could an object without stars still qualify? And if dark matter alone can sculpt gas into spinning disks, does that mean our universe is teeming with invisible versions of familiar structures, dark spirals, dark ellipticals, even dark counterparts to the Milky Way? The eerie possibility remains. We might be living in a cosmic hall of mirrors, surrounded by shadow twins we'll never fully see. Yet the search presses on, fueled by each new anomaly, like Dragonfly 44's bizarre dark matter dominance, or the Smith Cloud, a gigantic gas stream racing toward the Milky Way with no visible source. Every unexplained wiggle in telescope data could be another ghost waiting to be unmasked. And if one thing's certain, it's this: the universe has never been shy about defying our expectations. Dark galaxies might be its most audacious trick yet. While most dwarf galaxies seem destined to burn out quickly, either ripped apart by larger galaxies or blown clean by their own stellar winds, there exists a rare breed of cosmic survivors that have cracked the code of longevity. These resourceful dwarfs have mastered the art of galactic recycling, holding onto their precious gas against all odds and using it to fuel generation after generation of stars. Take the Phoenix Dwarf, a small galaxy near the Milky Way that shouldn't still be forming stars at all. Unlike its neighbors, which exhausted their gas supplies billions of years ago, Phoenix has been quietly birthing new stars in slow, steady pulses, some as recently as 100 million years ago. The secret, it's not just holding onto its gas, it's finding ways to recapture and reuse it like a cosmic thrift store. How does a galaxy with such weak gravity manage this feat? The answer lies in a delicate balancing act between destruction and renewal. When massive stars in the Phoenix Dwarf explode as supernova, they don't simply blast their gas into oblivion. Instead, the heaviest elements, oxygen, silicon, iron, sink back into the galaxy's densest regions, dragging cooler hydrogen gas with them. Over time, this recycled material pools together, forming new molecular clouds ripe for star formation. It's a galactic feedback loop. Stars die, enrich their surroundings, and in doing so, plant the seeds for their successors. Even the energy from those explosions seems carefully calibrated, too weak to sterilize the galaxy, but strong enough to prevent the gas from collapsing too soon. But Phoenix isn't alone in this cosmic economy. The WLM galaxy, another isolated dwarf, shows signs of multiple star-forming epochs separated by long quiet spells, like a galaxy hitting the snooze button between bursts of activity. Unlike the frantic starburst seen in other dwarfs, WLM star formation occurs in gentle waves, each one leaving enough gas in reserve for the next cycle. The key may lie in its isolation. Far from the gravitational turmoil of larger galaxies, WLM has avoided the violent mergers and tidal shocks that typically strip dwarfs of their gas. Instead, it's free to pace itself, turning its meager resources into a sustainable stellar ecosystem. What makes these recyclers so fascinating isn't just their thriftiness, it's what they reveal about the early universe. If small galaxies like Phoenix and WLM can retain and reuse their gas for billions of years, it suggests the first galaxies might have followed similar rhythms. Rather than blazing out in brief, brilliant bursts, they could have formed stars in patient, measured cycles, stretching their fuel across cosmic time. That changes how we model the universe's evolution, hinting that some dwarfs weren't just stepping stones to larger galaxies. They were resilient, self-sustaining islands of star formation all along. The lesson here is subtle but profound. In a universe where size usually dictates survival, these tiny galaxies have found another way. By turning their weakness, their low gravity, into an advantage, they've become masters of cosmic conservation. They don't dominate, they don't conquer, they persist. And in doing so, they prove that even the smallest galaxies can outlast the odds with nothing but patience, efficiency, and a little stellar ingenuity. The cosmic hierarchy we take for granted, planets orbiting stars, moons orbiting planets, takes on a surreal twist when galaxies start playing the same game. Astronomers have long known that dwarf galaxies often orbit larger ones like the Milky Way, like moths drawn to a flame. But in recent years, they've stumbled upon something even more bizarre: dwarf galaxies orbiting other dwarf galaxies, like celestial matryoshka dolls nesting deeper than we ever imagined. This phenomenon, dubbed satellites of satellites, upends our traditional view of galactic relationships, revealing a universe far more intricate and unpredictable than our models suggested. Consider the Large Magellanic Cloud, our Milky Way's most famous dwarf companion. For centuries, it was assumed to travel through space alone, tugged along by our galaxy's gravity. But in 2019, researchers poring over data from the Gaia Space Telescope noticed something peculiar. At least 4 ultra-faint dwarf galaxies weren't just trailing the Milky Way. They were locked in orbit around the Large Magellanic Cloud itself. These tiny cosmic hitchhikers, including Carina 2 and Carina 3, move in ways that defy simple explanations, tracing delicate paths around their already small host. The implications are staggering. If dwarf galaxies can have their own satellites, then galactic hierarchies might extend down further than we thought possible, blurring the line between satellite and independent in ways that rewrite cosmic taxonomy. How does such a fragile arrangement even exist? Gravity's grip weakens dramatically at smaller scales, making it astonishing that these faint dwarfs haven't been ripped apart by the Milky Way's far stronger pull. One theory suggests the Large Magellanic Cloud's dark matter halo, invisible but massive, acts as a gravitational shield, sheltering its own satellites like a cosmic umbrella. Another possibility: these dwarfs might be relatively new additions captured during the cloud's turbulent past. Simulations show that when 2 dwarfs pass close enough, the smaller can get snagged in the larger's orbit, creating a fleeting celestial partnership. Yet the fact that we've spotted multiple examples hints this might be more common than anyone guessed. The real shocker came when astronomers found similar structures beyond our local cosmic neighborhood. The dwarf galaxy NGC 2403, for instance, appears to host its own orbiting companion, a tiny galaxy dubbed NGC 2403b. Separated by just 60,000 light-years, a stone's throw in galactic terms, this pair dances in isolation, far from any larger galaxy's disruptive influence. Their existence suggests these micro-hierarchies aren't just flukes. They might be fundamental threads in the universe's fabric, woven into the cosmic web at scales we're only beginning to map. What makes these discoveries so revolutionary isn't just their oddity, it's the questions they force us to confront. If dwarf galaxies can have satellites, could those satellites in turn host even smaller galaxies? Where does the chain end? And if dark matter is the glue holding these fragile systems together, what does that say about its distribution on scales smaller than we've ever probed? Every time we uncover another layer of this cosmic nesting doll, we're reminded the universe doesn't just defy simplicity, it thrives on complexity, building order within order all the way down. Galaxies come in all shapes and sizes, but dwarf galaxies take cosmic diversity to another level. Some look like they were sculpted by an artist, while others appear as if they were tossed together at random. Unlike the elegant spirals or smooth ellipticals we're used to, these tiny cosmic structures defy classification, reshaping our understanding of what a galaxy can be. Consider the Fornax dwarf spheroidal, a near-perfect sphere of ancient stars orbiting the Milky Way. Its symmetry is so precise you could trace its edges with a compass. Then there's the Large Magellanic Cloud, a chaotic swirl of gas and stars that looks more like a spilled paint palette than a traditional galaxy, and nestled between these extremes. Oddities like Leo A, a faint, misshapen blob with no discernible structure at all, just a loose gathering of stars drifting through space like a celestial afterthought. What causes such wild variation? Gravity, or rather, the lack of it, plays a starring role. Massive galaxies like the Milky Way have enough gravitational muscle to mold their stars into orderly disks or smooth ellipsoids over time. But dwarf galaxies, with their weaker gravity, often lack the power to impose such structure. Without a dominant central force to organize them, their stars and gas are free to move more independently, resulting in shapes that range from haphazard to hypnotic. Take Segue 1, an ultra-faint dwarf so diffuse it barely qualifies as a galaxy. Its stars are scattered so thinly, they resemble fireflies in a vast, empty field. Then there's IC10, a starbursting dwarf where frenzied star formation has twisted its gas into chaotic knots, giving it the appearance of a cosmic tangle. But the real curveball comes from tidal forces. When a dwarf galaxy ventures too close to a larger neighbor, the gravitational tug can stretch it like taffy, warping its shape into bizarre new forms. The Sagittarius dwarf spheroidal, for instance, is being torn apart by the Milky Way's gravity, its stars fanning out into long, shimmering streams. Others, like the oddly rectangular dwarf galaxy Letta 740,000, seem to have been molded by ancient collisions, their forms frozen in time like celestial fossils. This raises a tantalizing question. Could some of these strange shapes be galactic scars, imprinted by violent encounters billions of years ago? Perhaps the most intriguing aspect of dwarf galaxy morphology is what it reveals about the universe's flexibility. These tiny structures prove that galaxies don't need grandeur to be fascinating sometimes. The most compelling stories are written in the chaos of the smallest cosmic brushstrokes. Whether spherical, shredded, or something in between, each one is a reminder that the universe has an endless appetite for variety. Amid the vast cosmic web, where giant galaxies cluster like bustling cities, astronomers have stumbled upon something far more unusual: tiny villages of dwarf galaxies huddled together in the void, completely cut off from the larger galactic metropolises. These isolated dwarf galaxy clusters, some containing just a handful of members, shouldn't exist according to our standard models of cosmic evolution. After all, gravity dictates that smaller galaxies should be drawn into the orbit of larger ones, like moths to a flame. Yet here they are, floating in the cosmic countryside, defying expectations and rewriting the rules of how galactic communities form. One of the most striking examples lies in the NGC 3104 group, a collection of at least 5 dwarf galaxies drifting together nearly 30 million light-years from the nearest massive galaxy. Unlike typical dwarf satellites which orbit giants like the Milky Way, these galaxies seem to have formed their own miniature society, bound together by mutual gravity. Even more puzzling, they're remarkably stable, with no signs of being torn apart by larger neighbors. It's as if they've built their own cosmic island, untouched by the gravitational tides that shape most of the universe. How did these clusters form? One theory suggests they're the surviving remnants of an ancient cosmic construction site, primordial building blocks that never merged into larger galaxies. In the early universe, dark matter's invisible scaffolding created dense patches where gas could collapse into small proto-galaxies. Most of these eventually merged into the giants we see today, but a few might have lingered on the fringes, forming tight-knit groups that resisted assimilation. Another possibility is even more dramatic. These dwarfs could be the scattered survivors of a larger galaxy that was ripped apart by tidal forces long ago, leaving behind only its toughest fragments. The real challenge lies in explaining their endurance. Without the gravitational anchor of a massive galaxy, these dwarf clusters should have dispersed over billions of years, their members drifting apart like leaves on a pond. Yet somehow they've held together. Some researchers point to dark matter. Perhaps these clusters are rooted in unusually dense knots of it, creating gravitational wells deep enough to keep their tiny galaxies in check. Others speculate that the dwarfs might be exchanging gas and stars between them, creating a self-sustaining system that resists decay. What makes these clusters so revolutionary isn't just their defiance of gravity's usual hierarchy, it's the questions they raise about the cosmic web itself. If dwarf galaxies can form stable, isolated groups, does that mean the universe has far more small-scale structures than we've accounted for? Are we missing entire populations of these cosmic villages, hidden in the gaps between the galaxy clusters we already know? Every new discovery peels back another layer of the universe's complexity, proving that even the loneliest corners of space have stories to tell. At the fringes of galactic classification lie the misfits dwarf galaxies so extreme they blur the line between cosmic categories. These outliers defy every expectation, holding records that make even seasoned astronomers double-check their data. Take M60 Satellite 1, the densest known dwarf, packing more stellar firepower into its tiny frame than should be physically possible. At just 120 light-years across, smaller than the gap between our Sun and its nearest stellar neighbors, this ultra-compact titan crams 10 million stars together so tightly that its core shines with the collective brilliance of 20,000 suns. Standing on a planet there, you'd see not a starry sky but a continuous golden haze, as if someone poured liquid sunlight across the heavens. Then there's the opposite extreme, Andromeda 19, a ghostly behemoth stretching over 60,000 light-years, wider than the Milky Way's disk, yet containing fewer stars than most globular clusters. This cosmic paradox drifts through space like a shattered chandelier, its stars spaced so far apart that entire solar systems could pass between them unnoticed. What keeps such a fragile structure intact? The answer lies in its monstrous dark matter halo, outweighing its visible stars by a factor of 10,000. A ratio so extreme it challenges our models of how dark matter binds galaxies together. But size isn't the only record being shattered. Segway 1 holds the title for darkest galaxy ever found, a place where just 350 feeble stars float in a sea of unseen mass. Calculations reveal that for every photon of starlight it emits, there are 100,000 suns worth of dark matter lurking invisibly beneath. Then there's Zwicky 18, the ultimate late bloomer, a dwarf that somehow avoided forming stars until roughly 500 million years ago, despite the universe being 13 billion years old. Its belated starbirth left it chemically pristine, with metal levels resembling galaxies from the cosmic dawn. Perhaps most perplexing of all is Willman 1, a galactic identity crisis masquerading as a star cluster. Smaller than many nebulae, it displays traits of both categories, tightly packed stars hinting at a cluster's origins, yet embedded in a faint dark matter halo characteristic of true galaxies. This cosmic chameleon raises profound questions. Where do we draw the line between a massive star cluster and a dwarf galaxy? The answer might rewrite our definitions entirely. These outliers aren't just curiosities, they're stress tests for astrophysics. Each one exposes gaps in our understanding, proving that the universe's creativity far outstrips our imagination. From dark matter dominatrices to stellar overachievers, these cosmic extremists remind us that the rules we've written are merely suggestions, and the cosmos loves to break them. Dwarf galaxies shouldn't last. In a universe where larger galaxies cannibalize smaller ones, where cosmic winds strip away gas, and where time erodes even the mightiest structures, these tiny stellar gatherings should have faded into oblivion eons ago. Yet here they are, scattered across the cosmos like cosmic cockroaches, surviving in environments so hostile they make the vacuum of space seem hospitable. Their secret, a mix of sheer luck, strategic isolation, and some clever cosmic loopholes that let them cheat destruction. Take the ultra-faint dwarf galaxy Tucana 2, drifting alone nearly 150,000 light-years from the Milky Way. By all rights, it should have been ripped apart by now, its stars scattered into the void. Yet it persists, clinging to a thread of dark matter so tenuous it defies explanation. One key to their longevity lies in their surroundings. Dwarfs that orbit massive galaxies like the Milky Way often meet violent ends stretched into stellar streams or devoured whole. But those that keep their distance, like the isolated Wolf-Lundmark-Melot galaxy, avoid these gravitational minefields entirely. Floating in the cosmic boonies, they escape the tug of war that dooms their urban cousins. Even more surprising are the dwarfs that survive inside galaxy clusters, regions so chaotic they've been called galaxy shredders. How? By moving fast. Some, like the Fornax dwarf spheroidal, zip through clusters at speeds too high for gravity to get a firm grip, like a motorcycle weaving through traffic. Others, like the dwarfs in the Coma cluster, nestle deep within the cluster's dark matter scaffolding, using it as a shield against tidal forces. Then there's the dark matter factor. Most dwarfs are swaddled in thick halos of this invisible substance, which acts like cosmic armor. Even when visible matter is stripped away, the dark matter remains, holding the galaxy's remnants together like an invisible skeleton. Consider Segway 1. A dwarf that's endured for billions of years despite being torn apart repeatedly. Its stars are so sparse you could fly through it for light years without seeing a single sun, yet its dark matter halo keeps it stubbornly intact. But perhaps the most fascinating survivalists are the dwarfs that adapt. Some, like Leo T, cycle through periods of star formation and hibernation, conserving gas like a desert plant saving water. Others repurpose their own destruction. When supernova blow out gas, it doesn't always escape, sometimes it falls back in, seeding future generations of stars. The Phoenix dwarf perfected this trick, turning its own explosions into a recycling program that's kept it alive for over 10 billion years. What do these cosmic survivors teach us? That the universe has more paths to longevity than we ever imagined. Size isn't everything. Ingenuity, location, and sheer cosmic stubbornness can be just as vital. And every time we find another ancient dwarf still flickering against the odds, we're reminded the cosmos loves an underdog. Deep within the ghostly wisps of dwarf galaxies, astronomers have uncovered an invisible force that shouldn't be there, magnetic fields powerful enough to sculpt entire galactic landscapes. These faint cosmic structures, often dismissed as too small and fragile to generate such energy, are crackling with magnetic activity that defies conventional astrophysics. Take the Small Magellanic Cloud, a dwarf galaxy neighboring the Milky Way. When researchers mapped its magnetic field using radio telescopes, they expected to find weak, disorganized signals, if any at all. Instead, they discovered a sprawling, coherent field stretching tens of thousands of light years, twisting through its gas clouds like an invisible cosmic spiderweb. The strength of these fields isn't just surprising, it's theoretically improbable. Here's why this baffles scientists. Magnetic fields in galaxies are thought to be amplified over time by a process called the dynamo effect. As a galaxy rotates, its swirling motions of charged particles act like a giant generator, strengthening weak primordial magnetic seeds into organized fields. But dwarf galaxies, with their slow rotation and sparse star formation, shouldn't have the necessary energy to sustain this process. They're like small towns trying to power a metropolis, except somehow they're pulling it off. The ultra-faint dwarf Leo P, for instance, has barely enough stars to light up its own gas, yet its magnetic field is strong enough to influence how those stars form. It's the cosmic equivalent of a candle producing a hurricane. The origins of these fields remain a heated debate. One radical theory suggests they might be relics from the early universe, frozen into place when dwarf galaxies first formed. If true, these magnetic fossils could preserve conditions from a time when the cosmos was just a fraction of its current age. Others propose that supernova explosions, though rare in dwarfs, might be seeding these fields by injecting turbulent energy into their gas like a single match setting off a wildfire in dry grass. Then there's the wild card, dark matter. Could mysterious interactions between dark and ordinary matter be generating unseen currents? The idea is speculative, but in a realm where conventional physics falls short, even the improbable deserves a look. What makes these magnetic fields truly extraordinary is their influence. In larger galaxies, magnetic forces play second fiddle to gravity, but in dwarfs, they might be the unseen architect shaping their evolution. Observations of the WLM galaxy reveal magnetic fields corralling gas into dense filaments, funneling material into regions where new stars ignite. Without these fields, some dwarfs might never have formed stars at all. Conversely, in galaxies like IC 1613, magnetic pressures appear to be blowing gas outward, stifling star formation like an invisible hand pressing down on the cosmic throttle. The implications ripple far beyond dwarfs themselves. If these tiny galaxies can sustain strong magnetic fields against all odds, what does that say about the early universe when all galaxies were small? Could magnetism have played a starring role in cosmic dawn, guiding the birth of the first stars in ways we've never considered? Every flicker of magnetic energy in these faint galactic embers is a clue, and a reminder that even the smallest corners of the cosmos hold forces vast enough to rewrite the rules. Scattered across the cosmos like pale ink dissolving in water, the ghostly remains of dwarf galaxies tell a story of destruction so complete it leaves almost no trace except for the stars. These aren't the grand, swirling structures we imagine when we think of galaxies. These are stellar streams, ethereal ribbons of stars stretched across thousands of light years, the only evidence that a dwarf galaxy once existed before being torn apart by gravity's relentless pull. The most famous example wins through our own Milky Way, the Sagittarius Stream, a river of stars so vast it wraps around our entire galaxy not once, but twice, like a cosmic serpent swallowing its own tail. Every star in this shimmering trail was once part of the Sagittarius dwarf spheroidal, a galaxy steadily devoured over billions of years until nothing remained but this shimmering funeral shroud. But how does an entire galaxy vanish so quietly? The process is both violent and achingly slow. As a dwarf galaxy orbits a larger host, tidal forces, the difference in gravity's pull from one side of the dwarf to the other begins stretching it like taffy. Stars near the edges get peeled away first, forming delicate loops and tendrils. Over time, these strands disperse, mixing with the host galaxy's halo until they're virtually indistinguishable. The denser core might hold out longer, but eventually even that succumbs, leaving behind only these faint stellar contrails. What's astonishing isn't just the destruction, it's the precision. The stars don't scatter randomly. They follow precise orbital paths, allowing astronomers to reconstruct the dwarf's original trajectory, like rewinding a cosmic film reel. Some of these ghosts are even harder to spot. Take the Orphan Stream, a tenuous chain of stars arcing through the Milky Way's outskirts. Unlike Sagittarius, it has no obvious galactic core left, just stars moving in perfect unison, their shared motion betraying their common origin. Chemical analysis reveals these stars are metal poor, a fingerprint of ancient dwarf galaxies that formed in the universe's youth. Their very composition is a time capsule, preserving conditions from long before the Milky Way took its current shape. Then there's the Phoenix Stream, a recent discovery that's rewriting the rules. Unlike typical streams which trace graceful curves, this one is kinked and twisted, as if the galaxy that birthed it didn't just fall apart, it fought back. Astronomers suspect the dwarf might have orbited through a clump of dark matter. the gravitational turbulence warping its stellar debris into this bizarre shape. If true, it's a rare glimpse into dark matter's hidden structure, using stellar streams as cosmic seismographs to map the invisible, the most haunting realization. We're likely standing atop a galactic graveyard. Simulations suggest the Milky Way should have consumed hundreds of dwarfs over its lifetime, their stars now woven seamlessly into our galaxy's fabric. Some researchers believe up to half the stars in our galactic halo might be stolen, their origins erased by time. Even our sun could be a descendant of these galactic nomads, its birthplace lost to an ancient collision we'll never fully trace. These ghost streams are more than just relics, they're active laboratories. By studying their subtle distortions, astronomers can weigh the Milky Way's dark matter halo, measure its gravitational pull, and even test alternative theories of gravity itself. Every faint ribbon of stars is a whisper from the past, reminding us that even in destruction, the cosmos leaves clues, if only we know how to look. Hidden in the turbulent hearts of colliding galaxies and along the faint tendrils of the cosmic web, astronomers are catching glimpses of something extraordinary, dwarf galaxies in the act of being born. These celestial nurseries, scattered across the modern universe, shouldn't exist according to classic models of galaxy formation, which suggest such tiny structures should have mostly emerged in the universe's chaotic infancy. Yet there they are, fragile knots of gas condensing into fledgling galaxies, offering us a front-row seat to a process we thought had ended billions of years ago. One of the most dramatic breeding grounds lies in the famous Antennae galaxies, two spirals locked in a catastrophic merger. Here, the collision's shockwaves have compressed vast clouds of gas into dense pockets, each one a potential dwarf galaxy in its infancy. Hubble's sharp eye has spotted dozens of these proto-dwarf, some barely 100 light-years across, yet already glowing with the first flickers of star formation. What makes them revolutionary isn't just their youth, it's their composition. Unlike ancient dwarfs, which are choked with dark matter, these newborns seem to form almost entirely from visible gas and stars, as if the universe is experimenting with a new recipe for galactic construction. Then there are the dark horse candidates, isolated gas clouds like the recently discovered Cloud 9 in the Virgo cluster. This frigid, hydrogen-rich blob shows no stars yet, but its mass and motion suggest it's on the verge of collapsing into a dwarf galaxy. Its sheer isolation defies expectations. Without the gravitational nudges of a larger galaxy nearby, how did it gather enough material to begin forming? The answer might lie in cosmic filaments, invisible rivers of dark matter and gas threading the universe. Where these filaments intersect, gas can pile up like driftwood at a river's bend, creating the perfect cradle for a new galaxy, no matter the epoch. Even more puzzling are the failed giants in places like the Leo Ring, a colossal loop of primordial gas orbiting two massive galaxies. Embedded within this structure are over a dozen dense clumps, each with enough mass to become a dwarf galaxy if they could only form stars. Some show tentative hints of stellar activity, while others remain dark, as if hesitating at the threshold of galactic adulthood. These stunted objects force us to ask, what's the missing ingredient that triggers a gas cloud to bloom into a full-fledged galaxy? The answer might rewrite our understanding of how all galaxies, big or small, take their first breaths. The implications are staggering. If dwarf galaxies can form today, it suggests the universe's creative engines never truly shut off, they just shifted gears. It also raises the possibility that some of the faint dwarfs we've long assumed to be ancient relics might actually be cosmic latecomers, born in the relative quiet of the modern universe. Every time we spot another of these celestial newborns, we're not just witnessing galaxy formation, we're seeing the universe's endless capacity for reinvention, proving that even now, in the cosmic afternoon, new worlds are still taking shape. Isolated from the cosmic chaos that shaped larger galaxies, some dwarf galaxies exist as perfectly preserved relics, time capsules holding conditions so pristine, they're essentially windows into the universe's infancy. Take the ultra-faint dwarf galaxy Segway 1, drifting nearly 80,000 light-years from the Milky Way. This cosmic hermit contains stars with metal levels so low, they're barely different from the primordial gas that filled the universe after the Big Bang. While galaxies like our own have churned through generations of stars, each one enriching space with heavier elements, isolated dwarfs like Segway 1 missed the party entirely. Their stars formed in a single early burst, then froze in time like insects trapped in amber, untouched by the chemical pollution that altered the rest of the cosmos. What makes these galactic time machines so invaluable is their chemical purity. In larger galaxies, supernova and stellar winds constantly recycle gas, peppering it with elements like carbon, oxygen, and iron. But in dormant dwarfs, the gas remained untainted. The stars we see today are snapshots of the universe's raw ingredients, their atmospheres preserving element ratios unchanged for over 13 billion years. It's the difference between studying a medieval manuscript that's been rewritten over centuries and finding one sealed in a vault, its ink untouched by time. The implications are staggering. By analyzing the faint light from these ancient stars, astronomers have detected unexpected patterns, oddly low amounts of certain elements that suggest the first supernova exploded in ways modern physics can't yet explain. Then there's the case of the dwarf galaxy Reticulum 2, a cosmic vault hiding an even more tantalizing secret, evidence of the universe's very first stars. Buried in its stellar census are a handful of stars with bizarre chemical signatures, trace amounts of europium and gold without the expected accompanying elements. This mismatched cocktail points to an exotic origin, pollution from a single, catastrophic explosion of one of the mythical population, 3 stars. These hypothetical giants, hundreds of times the Sun's mass, were the universe's first stellar generation made purely of hydrogen and helium, burning furiously and dying young. No telescope has ever directly observed one, but their fingerprints might finally be preserved in these dwarfs' chemistry. Finding them would be like uncovering a fossil of the cosmos's first light. The true power of these time capsules lies in their isolation. While most galaxies cluster together like cities, constantly exchanging gas and stars, a few dwarfs, like the newly discovered Cetus II, float in the cosmic boonies, so remote they've barely interacted with another galaxy in billions of years. This solitude is their superpower. Without gravitational disruptions or mergers to stir their gas, they've avoided the recycling that erased pristine conditions elsewhere. Even their dark matter halos might be untouched, preserving the original clumpiness of the early universe's scaffolding, yet these cosmic relics are disappearing fast. As telescopes grow sharper, astronomers are realizing many ultra-faint dwarfs are on the brink of dissolution, their stars barely held together by wispy dark matter. Some, like Triangulum 2, show signs of being actively shredded by the Milky Way's gravity. Others are so diffuse they're practically ghosts already. It's a race against time to study these galactic fossils before they vanish entirely, taking their secrets with them. Every photon we capture from their ancient starlight is a message from an era before planets, before galaxies as we know them, when the universe was just learning how to build. What if we told you the golden age of dwarf galaxy discovery hasn't even begun? Right now, tucked in laboratories and clean rooms around the world, the next generation of telescopes and space missions are being polished to perfection, each one capable of revealing dwarf galaxies in ways that would have been pure fantasy just a decade ago. Imagine instruments so sensitive they could spot a lone star flickering in a dwarf galaxy halfway across the observable universe, or space observatories that map dark matter's invisible fingers gripping these tiny cosmic islands. This isn't science fiction, it's the imminent future of astronomy, and it's poised to tear the veil off dwarf galaxies' deepest secrets. First in this cosmic arsenal is the Nancy Grace Roman Space Telescope, set to launch by 2027. While Hubble showed us the beauty of distant galaxies, Roman will act like a celestial census taker, scanning vast swaths of the sky with a field of view 100 times wider than Hubble's infrared camera. This means it could discover thousands of new ultra-faint dwarfs lurking in our cosmic backyard galaxies so dim and diffuse they've slipped through every observational net until now. But Roman's real superpower is its ability to map dark matter in unprecedented detail by observing how light bends around these dwarfs. For the first time, we might see whether the missing satellite problem stems from galaxies being too dark to spot, or if dark matter behaves in ways our models never predicted. Then there's the Vera C. Rubin Observatory, a ground-based behemoth in Chile that will start its 10-year legacy survey of space and time in 2025. With a mirror the width of a tennis court and a 3,000-megapixel camera, Rubin will capture the entire visible southern sky every few nights, creating a time-lapse of the universe. This relentless gaze will catch dwarf galaxies in the act of cannibalizing each other, measure their erratic star-forming bursts in real time, and possibly spot the first confirmed dark matter-only galaxies through their gravitational fingerprints. Rubin could even solve the riddle of why some dwarfs orbit in planes. By tracking their movements over years, we'll see if these alignments hold or if they're fleeting cosmic illusions. But the crown jewel might be the European Space Agency's Euclid mission, already sending back data from its orbit 1 million miles from Earth. Designed to create the largest 3D map of the universe, Euclid's infrared eyes peer through dust that obscures dwarf galaxies' faintest stars. Early images hint at something revolutionary: dozens of potential dwarf galaxies floating in the voids between galaxy clusters, places where theory says they shouldn't exist. If confirmed, these isolates could force us to rethink how galaxies form in the universe's emptiest realms. On the horizon loom even wilder possibilities. The Square Kilometre Array, a radio telescope network spanning 2 continents, will detect hydrogen gas in dwarfs so distant their stars are invisible, revealing galaxies in their infancy. The James Webb Space Telescope, though already operational, has barely scratched the surface of dwarf galaxy archaeology. Its upcoming deep field observations could uncover population 3-star signatures in ultra-faint dwarfs, essentially letting us watch the first stars ignite. And future gravitational wave detectors like LISA might sense the ripples from merging dwarf galaxies' central black holes, events too subtle for current instruments to catch. What makes this technological leap so thrilling isn't just the promise of new discoveries, it's the certainty that dwarf galaxies will surprise us. Every time humanity has built a better window into the cosmos, these tiny galactic underdogs have upended our expectations. They've proven that darkness can outweigh light, that size doesn't dictate destiny, and that the universe's quirks often hide in its quietest corners. As these next-generation tools come online, one truth becomes clear. The story of dwarf galaxies isn't just being written, it's being rewritten, with every observation challenging what we thought we knew. The greatest revelations aren't behind us, they're hiding in the data streams of tomorrow's telescopes, waiting to shatter our assumptions once again. From ghostly galaxies made almost entirely of dark matter to cosmic rebels that somehow form in isolation, dwarf galaxies have shattered every expectation we've ever had about the universe. These tiny structures, once dismissed as celestial afterthoughts, have forced us to rewrite the rules of physics, rethink the nature of dark matter, and even question what it truly means to be a galaxy. Who could have imagined that the smallest galaxies would hold the biggest surprises, like the ultra-diffuse galaxies stretching as wide as the Milky Way with just 1% of its stars, or the tidal dwarfs that form from galactic wreckage without any dark matter at all? Then there's the spine-tingling mystery of the missing satellites, the synchronized orbits of dwarf galaxies moving in eerie harmony. and the ancient, metal-poor stars preserving the universe's earliest chemistry like cosmic fossils. Perhaps the most humbling lesson is how these discoveries keep proving how much we still don't know. For every answer dwarf galaxies provide, like revealing the violent mergers that built today's giant galaxies, they throw open a dozen new questions. Why do some lack supermassive black holes? How do dark matter halos shape them so differently from larger galaxies? And could those invisible, starless dark galaxy candidates be lurking everywhere, rewriting the cosmic census? What once seemed like a niche corner of astronomy has become a revolutionary frontier, where every faint smudge of light might hold universe-altering secrets. So, which discovery blew your mind the most? Was it the dwarfs that form in isolation, defying gravity's rules, the ones that blow themselves apart with supernova winds? Or the ones that might be made entirely of dark matter, invisible yet shaping the cosmos around them? Drop your thoughts in the comments, because in a universe this strange, the best conversations are just beginning. And remember, the next time you gaze at the night sky, those faint patches between the stars, they're not empty. They're teeming with dwarf galaxies, each one a reminder that the universe's smallest wonders often hold its grandest truths.